go to full screen. Good. So yeah, thanks for. Are you ready? Yeah. Okay. Thanks for having me here. I'm here to present the work of Shreya and Yulia, who are two honors master students who in the Faculty of Architecture, who over the 18 months period of time, were doing this project in addition to their normal coursework, in addition to their thesis, and unfortunately couldn't be here today, but I really want to represent their work on human-robot collaboration in digital fabrication for architecture. The first paper by Shreya is about, or led by Shreya, is about the shared authorship, so how you create a shared authorship between human and machine. And the second is about the role of interface, whether that's a VR or haptics or whatever that might be, and how that has a role in the human-robot collaboration. And these are also intersecting concepts, but we wrote two separate papers because they were both leading their own honors project. Also should mention Angelina, who's a postdoctoral researcher involved with the work as well. So I'll try to do justice to the work as best I can. Yeah, we're looking at digital fabrication as a transformative method in architecture. I really want to emphasize the design aspect here. So a lot of the work around digital fabrication has an intersection with the kind of aesthetics and the design space. And so we're not talking about bricklaying robots, but about robots that are also involved in architecture of some way. That particularly comes because the project is funded by the National Center for Competence in Research in Switzerland, hosted at ETH, focused on digital fabrication in architecture. We know the construction industry challenges, safety, inefficiency, costs, and we see this rise of HRC, and we wanted to study how it's coming together. In particular, I think a key point here is that we have a huge number of construction deaths, and construction safety is really key. We have unstructured environments, and now we say we want to introduce robots into those environments. So we really need to understand the nature of the work. Also, automation, it requires this level of precision, but we also know that autonomy fails when you have these complex and material-rich environments. So we need to kind of understand along this continuum of fully programmed robotics in cells like we have in manufacturing. We're going now towards this fully collaborative level of human-robot collaboration. For the first paper, the research questions and aims was about agency. So how do we understand robotic agency? What does it mean for robotic agency in the context of projects? So how do we define robotic agency? What are the implications of shared authorship? So in architecture, you have kind of this authorship of the human designer, but what happens when a robot begins also contributing to the authorship? And how does it affect the roles and the responsibilities of the stakeholders in the process? So that's the questions we were answering on the agency side. On the interface side, we were curious about how the interface affects the communication. There are many different ways in which you can design a shared interface between human and machine, and we were curious about the implications of that design. Does it determine the frequency of the interaction? To what extent does interface influence the levels of engagement and task distribution? So how often and which tasks are assigned? And in what ways does interface shape the workflow in open-ended design processes? I'll go quickly through here, but we looked at a number of different key studies, and I'll just highlight a few limitations. In COPE, we saw that there was a lack of understanding the changes in dynamic materials as the material changes in robotic fabrication. How does HRC adjust? In the study by Janko, we saw that we weren't thinking about the shifts in agency. Agency might change during the course of construction and design and construction, and also thinking about the open-ended material logics that might exist. On the interface side, Villani, we saw one limitation was it oriented towards a very structured environment with repetitive tasks, so we're not talking about the unstructured nature of a kind of construction site. The work by Parasheko was also focused on precision, but we didn't really talk about human perception, decision-making, and engagement. And with Brun, we saw that it was conceptually strong, but we were looking at kind of the multimodal interfaces. Now, these papers were all very inspirational for us. These were just some of the limitations we saw in the current literature. Methodologically, that was already the literature view, which I just described. But we conducted a set of comparative case studies. So we looked at 3 digital fabrication and architecture projects located at ETH Zurich. The first one is, I'll explain all 3 in a moment. but we were really curious because they were kind of originating from the same research labs, so they were coming from the same origins, but they also had different characteristics which were interesting for us to study. The researchers conducted 15 interviews. It's important to note that these are mostly with researchers that they're interviewing, so there's not practicing architects, they're not interviewing construction workers per se, but there are researchers, but also engineers and technicians that they're asking about how they deal with the HRC. And they also generally spoke with 3 kind of socio-technical experts, so people that are thinking about this already within the context of the research, but are not necessarily working on these specific case studies. Here are the 3 case studies. I'll explain them in detail in a moment. So the first one is tie a knot, the second one is interactive robotic plastering, and the third one is autonomous dry stone wall construction. The first case is tie a knot. I don't have a video for this one, but here I can kind of explain it, is that you have a mobile robot who is designing alongside with the human. The human is there to, ideally the human is there to kind of design and place the elements, but there's a kind of audiovisual directive that's coming from the robotic system. And the goal here is kind of human-robot teaming. So you have this kind of shared connection between the placement and the tying of the knots. I'll say more about what happens when I get to the findings, but I just want to give you that's the overview. The second one is, let's see if this works. Yeah, interactive robotic plastering. Here the video also kind of shows it better than I can describe it in text, but it's the idea that you have this plastering process, which is drawn with a virtual reality, or in this case with kind of a wand, which is tracing where the placement of the plaster might be and to what's the degree and density it might exist. And then you're able to have a robotic spraying process which follows this, but it's also not kind of your standard plasterboard application, but it has some type of architectural design or aesthetic that's emerging. And there your interface is your handheld visual display, right? So you're moving this around. And then the third one is the autonomous dry stone wall construction. In this one, it's the construction of a circular rock wall where the Menzimuk is creating 3D map you can read as well. So you're scanning the stones as you're picking up. You have a target design, and you're placing it's autonomously placing the stone based on the location in which you want to place the different pieces. So in other words, you have not predetermined which rock goes where, but in the process of building the wall, you're scanning and selecting and placing the walls. In the interface then you have the robot which is sensing the material, and there's a human operator, but there's quite a big separation in this case compared to, for example, tie the knot where they're really working together. Here it's a lot more separated between the two. So if we would summarize why we want to look at these 3 cases. So in tie a knot, you have the iterative adjustments of knotting joints and components positioning. And you also have 2 to 2. So you have 2 humans and 2 robots on the site, and it's in the lab. And the second one is the plastering. You have 3 humans to 1 plastering robot, also in the lab. And the last one is about the material selection. You have 1 robot and 1 human that's not really on the site, but the robot is there on the site, and the human is there kind of as a technician, you could say. The 2 students, that's Julia and Shreya, they're really the stars here. They went to Zurich from Delft. They went and attended a conference, but also at that time conducted a number of interviews with the researchers. They asked a series of questions here. So can you think of instances where the capabilities or limitations sparked new design ideas? So this is the idea of an emergent design coming from the interaction with the robot. Can you describe your interface experience with the interface implementation? So here, was the path planning tool user-friendly? Are you able to adjust? What are the kind of deviations from your plan? And finally, how do you interpret the situations where the robot didn't perform, right? So if the robot had a specific expectation from the side of the researchers, what situations arose, and how did that change your assembly and your sequencing processes? So this is a comparative case study, qualitative research. They developed a coding schema. I won't go into too much detail, but they started to look at things like, for example, you can see here under the interaction roles, is there turn-taking, goal setting, human as supervisors, peer, and et cetera, and use this as a basis for analyzing the 3 case studies. I just want to highlight a few of the key findings. You can read the two papers if you want to dive deep into the topic. But on the topic of robotic agency and task allocation, I think this is an interesting one. So there's this idea of turn-taking. So the robots are placing and holding the elements, and the humans are responsible for making these connections, right? The dexterity of the human fingers are good for this. And the robots were expected to stabilize the structure, but that's not what happened in reality. So this quote is, "We realized mid-process the knots were slipping under stress, so we had to intervene and reinforce them before continuing," right? So here was an expectation about how the task distribution would have been a certain way, but because of the nature of the work, in the process they found that this wasn't quite working in the right way. So this is also, you could generalize this to say when you have emergent structural behavior that might come from a non-predetermined design, you have to really think about the nature of HRC so you can make a process change in the midst. Another quote, which we don't have here, "The robot could tighten the knots, but the humans had to make constant adjustments even back into the original knots to maintain the balance and the tension." Continuing on the question of agency, this is for interactive robot plastering. You have this time-sensitive plaster. If anybody's ever worked for plastering, you know that at minute 5, it's very different than minute 30 about the mix and the feel of the plaster. And that requires rapidly changing material states, so things are changing really quickly, and you need continuous intervention to adjust the robotic operations. So I like this quote. It says, "The robot might spray evenly, but only humans could assess the surface texture and the surrounding conditions to make the final adjustment." So you can have whatever predetermined course of action you want, but the human was constantly having to go back and take agency over some decisions, and so some robotic agency decisions were not helpful for the final design of the project. So here we see a lot of human judgment, especially in manual corrections and the interdependency with material properties in HRC for construction. And finally, so I'm going to go back, then we'll go to interface next because I'm doing the two papers. So this is really on the agency. The last one is the autonomous drywall stone construction. One quote was, before I get to this quote, they said that achieving full autonomy would require perfect sub-millimeter scans of every stone, which they weren't able to have. The irregularity of the natural stones was challenging. There was also the times where the terrain was so uneven that they had to guide the robot manually to prevent the misalignment. So their expectations weren't always coming together. The system was able to make very good placements from the structural design perspective, so the decision-making was really good, but the human was really the one making the final decisions, thinking about time constraints and other unpredictable factors. And they said they have to often incorporate larger stones to accelerate construction in some moments, right? So maybe because of the schedule they're falling behind, so they're actually picking larger stones and manually overriding what might happen. And there was also microfracturing, which was unforeseen. So the idea that if you really put a stone in the wrong place and you had these microfractures, it could cost you a lot of time because then you have to go back and remove all the pieces that you stacked on top. So this was also something that required them to rearrange and recalibrate on the agency side. Good. So to summarize this first paper on the agency, we had the human robots as the human instructor and the robotic executor. There was this kind of idea of leftover automation. So robots are performing the tasks and the humans do the really boring stuff, which is adjusting the details and tightening the knots. And this is something maybe we want to think about, is this the way we want to design work systems? The human was the instructor, so defining the robot operation material flow, using an AR and audio-visual directives, and they were co-located. The second one, we really noticed this is more of like a human peer robot collaborator. So the plasterer was really like another person on the team plastering, or at least you could think about it that way. There was knowledge and creativity allocation. So the humans were doing the patterns and the robots were a bit more executing the work. And so we saw a bit more in this one, human as a peer and equal contributions. I'll say more about the interface in a moment. And then in the last one, you had the human supervisor and the robotic worker. So the human was doing the takeover, right? The error correction. When they see problems, they kind of intervene as a kind of manager. And the human then is setting the large-scale objectives and monitoring to see if the performance is being done. So I want to save the decision support because I think that's in the other paper, which is about the interface. So here we have some insights about kind of trust, so trust in the interface and in the machine, the feedback and the cognitive load. So how is it that practitioners and, well, in this case, researchers, dealing with the cognitive load of robotic systems, and how can interface either ease or exacerbate some of the challenges there. I like this quote, if you have too many options, you don't have the time. So they try to take the cognitive flow off from the human while still allowing them to be as creative as possible. So this is the intention of the robotic system designer, is they have a very complex structural design, and the structure is being recalibrated as the design emerges. But it also creates this cognitive overload for the users, because you have so many options to choose. So they're actually also trying to limit the variability there. So there's really a continuous timeline of control that happens in the virtual space that needs to be considered in the design. In the interactive robotic plastering, there was a really good communication with the user to visualize and modify the trajectories. And then we already mentioned there was this need for feedback quite often. And one thing that was also interesting was the emergence of both visual and audio feedback as well. So this quote saying, it's necessary to have a combination of visual and audio feedback. The more you speak to the sensors of the human body, the more you reach full intuitive interaction. And that was a nice insight to see, and it kind of makes sense. Of course, we're going to do well if you have both the visual, but also you have audio feeding back. And I don't recall exactly what the audio feedback was that they designed in this system, but they used some kind of alert when things were kind of not working well instead of just a visual interface. And then finally, for the last one, we mentioned these irregularities, the environmental changes. And here they had in the visual interface something that would show all the things like the stones that were available. It was a lot about giving the visual features so that the manager, the orchestrator could say, okay, yeah, this is the plan that came out, and so they called it a digital twin, so you can monitor that over time, so you can see how things are going, and that allowed them to the human to kind of be in a monitoring position as an interface manager for that process. I'll wrap up with a few last points. For this paper, the key, we saw the interface really enabled dynamic task allocation. When you had more multimodal systems, you had more engagement of the workers. I'll take a moment to say the real-time feedback is really key here. You have the feedback, feed now, and feed forward. So this really needs kind of explainability and transparency, and we saw that critical across all three cases. So that goes all the way back to the multimodal feedback. So can we have haptics, visual, audio cues? These kind of considerations for design of these systems becomes really important. And that builds the trust. So that was one of the big takeaways there. In terms of the cross-case insights, we saw that there was adaptive interfaces, so that allowed that for more flexible workflows, intuitive tools, robotic agency, context-specific, and shared decision-making led to the perception that there was better results. For the sake of time, we have a few other things. So we had some cross-case insights. I like this table in particular, where you can kind of see they tried to map the level of human contribution and robotic contribution across adaptation, execution, and design and planning. We also had a number of barriers and design challenges. And if I would summarize, what we did with the first paper, so the shared authorship paper, we were able to try to incorporate a comparative framework to analyze robotic agency in these open-ended in situ construction settings where design was really critical. We see shared authorship as a negotiated dynamic between the human and the robot across the design, execution, and adaptation phases. And we had attention to these material responsive workflows and co-located collaborations, as we saw in the first two cases. In the second paper about interface, we feel like there's a lot of papers in HRC that address communication modalities or interface typologies, but we also see that these kind of really fall short of explaining how interface selection actively shapes the engagement, task distribution, and collaborative decision making, right? So What our critique from doing this work is that we often see interface as an add-on to the design of a robotic system, and we would argue that it actually becomes fundamental and necessary to be considered in the entire design of the joint cognitive system. And in this particular paper, we looked at adaptiveness, the workflow continuity, balance interaction, and also how the interface helps specifically with facilitating trust, the air handling, and the skill translation. Future research on the agency side, we want to look at continuing the development of framework for assessing robotic agency. We'd like to continue to understand the implications of shared authorship, especially in architecture, where that's very important. I think for construction tasks, it's less important, but you also can argue there is something inherent about the digital craftsperson that's quite important to understand. And we continue to look at the stakeholder roles and how this open-ended design process changes stakeholder roles and responsibilities. What is the role of an architect when the design is not predetermined before you start? What is the role of engineering and also permitting and regulations when you don't know exactly how the structure will be designed if you have a kind of collaborative approach? And then on the interface level, we still want to further understand these different modes and models of collaboration. In particular, we've been utilizing joint cognitive systems theory to understand how the different collaboration modes influence interactive frequency and collaboration. There's more work that can be done on interface design always, and there's importance on the workflow, and there I'm a big believer in this type of work, and also even going towards ethnography to really understand the nature of which tasks are done, especially in these exploratory design processes. Good. If I leave you with three things from today and my double joint presentation, interfaces are not peripheral, they shape the collaboration, so you can't put interfaces as an extra add-on. It actually shapes the nature of the collaboration itself. Robotic agency is flexible and must remain human-centered. So robotic agency is a dynamic and changing thing, and sometimes we're giving much more agency to machines and sometimes much less, but we have to think about robotic agency. And then we see a lot of opportunities for further research from the scalability, the regulations, developing our frameworks we mentioned, and also thinking about workforce training, et cetera. So thanks for your patience with my double presentation, and that also leaves us, let's say 5 to 7 minutes for Q&A. So thank you very much.